Alright, and we've been studying the derivative at a point, and now what we want to do is we want to obtain the graph of a derivative in general, so for all domain values if possible. And we begin this by recalling that the derivative is the slope of the tangent lines at a point. Okay, so really we're saying the graph of f prime, the derivative of f, is just the graph of the slopes of the original function. Okay, so if we look at an example graph here, so f of x is given. It looks to be linear. We want to sketch the graph of f prime. Okay, so what I'm going to do is I'm just going to look at various nice points. So I'm going to, let's see, this is a nice point at 0, 0. Let's see a couple other ones that land on nice coordinate points or coordinate grid points. So maybe these 5 points. Okay, and I need to consider what the tangent line is at each of these. So if I draw the tangent line, it's going to be something like that, or actually I could probably just draw right through it if I wanted to. That would be another tangent line. It only intersects the graph once. Okay, but now I want to look at this point. What is the slope of that little red line that I just drew? Well, I would say, now this is really a matter of estimation. That looks to be about a slope of, say, 2 to me. So I'm going to put at my x value stays the same at 2, and I'm going to put now a dot at positive 2, and so I'm saying that the slope becomes my new y value. So my dot goes at 2, 2. Now at 4, comma 8, this tangent line, and I'm going to draw it right here. That's a little off, but that tangent line looks to also have the same slope as this tangent line. So I'm going to say that that has a slope of 2. So when x is 4, the slope at 4 is also 2. Okay? And at 0, I'm going to draw my tangent line. Okay? Again, not a perfect line. But that slope appears to have the same slope as these other tangent lines. So I'm going to put that dot at 2 as well. So the slope of f at 0 is 2. Okay, and then similarly, I'm gonna the other ones will turn out to have an estimate of around 2 as well. Okay, so really what I'm saying is here, this horizontal line is the sketch of f prime of x. So this linear function, and I will tell you that the purple line is a linear function. The linear function, its derivative results in a straight line. And this makes sense because we know that a linear function has a constant rate of change, meaning that the derivative should be a constant value. And this time we put it at 2. We could have estimated it to be 3 or 4 or something, but either way, we know that it's a constant value for the derivative. Okay, so this seems easy enough. Let's continue on, and we see this little bit more complex function. It's actually given to us, and so we need to sketch the derivative of this, and well, the other one was easy because we had nice known points. This one, it looks to be a little bit more complex, so what do we do? Well, in the module notes, we actually have these tables and then this other descriptive paragraph given in the notes. But what's really nice about this is it tells us when f of x is increasing, and actually I want to start when f of x is horizontal. Okay, horizontal, that means its rate of change is 0. So that would be, think of this as a slope of 0. Okay, so the rate of change is 0. If it is decreasing, i.e. the slope is negative at the point, well then f prime is negative. If it's increasing, positive, and then similarly with all these. If we have the function being straight or behaving linearly, as we saw in the last example, that means that the f prime is going to be horizontal, so straight line across. And these are all just reiterating these in more of a descriptive form. One key thing that I recommend, and you don't have to do this, but I find it useful, is to identify the slopes of f of x that have a slope of 0 first and plot those points. Okay, so if we go back to our example, we're going to try this again. So I'm going to look for where the slope is 0. So it looks to be 0 here, down here, here, kind of where it flattens off. Here and here. And certainly I'm not going to plot all these, but for each of these places where it is or where it has a slope of 0, that means my y-coordinate is going to be 0. Remember, the y-coordinate now is the slope at the point. So the slope, and I'm going to put this at 5, is going to be right about there. This is at -2. Is it 0? Okay, well, this is rather easy. It's going quickly. So I'll just finish this off here. Okay. Now, we need to determine where the rest of the graph is. Okay, so before this, let's just kind of take it chunk by chunk. So between each of these, these slopes are all positive. Okay, even though it's starting at negative here, these slopes are all positive, but they're decreasing to 0, right? So what we're saying is that the slope looks something like this. Okay, and then after this point, the slopes are all negative because it's going downhill. So it's decreasing, 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 and it's still decreasing, but it decreases so that it's close to 0. So what happens is it decreases, comes back up. It's still decreasing, keep in mind, it's still negative. The slope is still negative, but then it comes up and hits 0. Okay? So even though it's constantly decreasing, but the values, the slopes, end up making this U-shape. So it's maybe -1, and then it decreases, okay, and then but it's still decreasing, just in magnitude it's less. And then between, say, -5 and 2, this is positive. Okay, so it's positive, but again, it's increasing in magnitude, and then eventually it has to get back to 0. So it's going to increase, but then it has to decrease back down. It's still positive, keep in mind, but in magnitude, in size, it's decreasing back to 0. And then here it's negative, so it's going to look something like this, coming back up to 0. And then here it's increasing, so it should be above the x-axis. But again, it increases, so it's above the x-axis the entire time, but it increases in size and then decreases back to 0. And then eventually, this is all a negative slope, so it has to lie entirely below the x-axis. Comes down, and then in size comes back up. Oh, ignore that. It's a little bit of bad drawing. And then now after, and I'll just finish this off here, but this is going to be large positive slope, decreasing back to 0, and then after 8 it'll decrease. The slope is all negative, so it's going to decrease to 0. So it's going to look something like this. Let's undo that. So it's going to increase. Bad drawing. Let's try that again. So it's going to increase, decrease, and then do something like that. Okay, so this is just a rough sketch. And that's all that is being expected here. You can, of course, obtain the actual graph by using Wolfram Alpha. So if we actually look at the graph, and here's the derivative if you're interested, it should be y prime. But the graph is in red here, and so we were relatively close. But now keep in mind, and I'm not going to answer these questions, but we can ask some questions with this graph. So first one being, what intervals is it increasing and decreasing for the original function? When is the rate of change in f of x 0? Okay, so think that would be when is when do you cross the x-axis for the derivative? And then lastly, and probably the most challenging question, is what intervals is the function f prime increasing and decreasing? Okay, so you actually have to look at f prime now and consider, okay, when is it increasing and when is it decreasing? So, for example, it would be decreasing, say, between negative 3.5 and negative 1. Okay, so keep those things in mind. Plausible test questions. That is a brief introduction on how to obtain the graph of the derivative from the original function. Next video we'll look at actually obtaining the function for the derivative of a known function. Alright, so stay tuned.